So, very good afternoon to all. So, I welcome our next expert, Dr. C.C. Reddy from IIT Roper. I welcome Dr. Piyush Verma and other participants in this second lecture of first day. So, before we start our lecture, let me briefly introduce our expert to the participants. So, now we have with us Dr. C.C. Reddy from IIT Roper. Dr. Reddy did his BTech in Electrical Engineering from Government University, College of Engineering, Hyderabad, India in 1995. After his BTech, he worked as a lecturer and assistant professor in Electrical Engineering under JNTU University, Hyderabad, India. After his ME and PhD from Indian Institute of Science, Bangalore in 2005 and 2008, Dr. Reddy has joined J Power System Corporation, Hitachi, Japan, a joint venture company of Hitachi Cables Limited and Sumitomo Electrical Company, and served as a senior R&D engineer in its ultra-high voltage research lab till 2011. Currently, he is working as associate professor at Indian Institute of Technology, Roper since 2011, and he is associate dean of student affairs. He is an associate editor of IEEE Transaction on dielectrics and electrical insulations. He is a member of Bureau of Indian Standards Committee on Dielectric, member of Board of Studies of several universities in India. Dr. Reddy had participated in academic industry collaborative research in Japan with several universities. He had also participated in the deliberation of Technical Standards Committee on space charge measurement in electric materials. Dr. Reddy has published many papers in reputed journals and conferences, that is IEEE, IAT, IEET, J, in the field of nanodielectric, power cables, power transformers, mechanism of breakdown, space charge and conduction in dielectric materials. He has guided 4 PhD students in their defense and currently guiding 10 PhD scholars apart from several MTech and BTech students. He has authored a book on reliability and life estimation of power equipments with New Age International Publisher. He is working and worked on several projects with private industries like Reliance, Adani, KEI Industries, Apart Industries, etc. Apart from public industries such as CPW, CPRI, etc. He has been the organizing chair, general chairs, and technical program committee member of many conferences in India and abroad. Dr. Reddy, having a very wide teaching and research experience in the universities of India and abroad, I am sure these lectures in this STC will be very informative and knowledgeable. So now, may I request Dr. C.C. Reddy to please deliver his talk. Welcome once again, sir. Please start your lecture.
Thank you, Dr. Balvinder Raj, and thank you, Professor Piyush Verma, for inviting me for this lecture series. Yeah, that's very long introduction. Thank you. So now I will start my presentation. So good afternoon, everyone. The title of this presentation is Circuits for Generation of High AC/DC Switching and Lightning Impulse Voltages. So as part of short-term course at NITTER. So I am from IIT Roper and has been introduced already. So these are my contact details for any future interaction if you would like to have, or any questions if you would like to have, you may ask me. So the circuits presented in this presentation are from high voltage engineering fundamentals. This is the textbook I follow for teaching high voltage circuits. Kofel and Jung. So let me start my presentation. This is the beginning. Voltage stresses. High voltage means the power systems normally if they are operated at higher voltages, with the increasing voltage the losses gets minimized, and apart from several other advantages such as transmission of higher amount of power over longer distances is possible using high voltages. So the current will get reduced because V into I is power, of course, V I cos theta. So for any cos theta power factor, V into I represents the power. So if we increase the V, obviously I will go down. So if I goes down, I square R is the loss on the transmission line. Of course, apart from this, our transmission capability also increases with voltage. So transmission systems are that is why at higher voltage level. Why not at a distribution voltage level? That is what we are getting at home, 230 volts. So we cannot transmit the power at same voltage level. We need to transmit the power at higher voltages to decrease the losses and for higher power transmission capability. So when transmission lines are operated at higher voltages, naturally different kinds of voltage stresses will be there on the transmission line. So normal operating voltage, this is the operating voltage of the transmission line. Normally, this does not severely stress the transmission line or systems, except under polluting conditions. Polluting conditions mean, such as rain or some pollution, air pollution or fog, etc. Under these conditions, even under normal operating voltages, certain stresses will be there on the transmission line or insulators, etc. But what is the importance of normal operating voltage then? It determines the size or dimension of the power system. So this is the significance of normal operating voltage. But apart from normal operating voltage, there are over voltages. Over voltages, these are actually two kinds of over voltages are there. One is external over voltage, another is internal over voltage. External over voltages are due to lightning. That is, naturally occurring phenomena when clouds are charged. Then they discharge to the transmission line, or of course, if they discharge to other objects, we are not concerned. But if it discharges to a transmission line, so a lightning wave is induced on the transmission line, which moves in either direction and may hit this is how external over voltages will occur. And there are, apart from that, internal over voltages, IOV. This is due to switching condition or, fault conditions or any fluctuations will cause certain oscillations on the transmission line. These are over and above the normal operating voltages. These two actually, even external voltages or internal voltages are over and above the operating voltages. And let me draw a little bit. If this is the pure sinusoidal voltage waveform, so what will happen? Whenever a lightning strikes, there may be a peak like this. Or whenever a switching occurs somewhere, so you will see oscillations and then oscillations will die down. So like this, these over voltages will cause problems on the transmission line. So with higher voltage levels, what will happen? So the lightning voltage is the maximum magnitude is fixed. So the switching, this is switching. The second one is switching. This is lightning. First one is lightning. So the switching operations, the switching over voltages assume importance as the voltage level increases. So, for example, more than 300 kilovolts roughly, so switching will dominate over the lightning. So we have to concentrate on switching more than lightning if the voltage levels are more than 300 kilovolts. Now internal over voltage, that is switching voltage, magnitude depends on the rated voltage of the system also, power system, and instance at which a change in operation condition occurs, whether you have switched it on at zero crossing or at 90 degrees phase angle. So all this will cause the over voltages, decide the over voltage magnitude. And the complexity of system, how complex the system is, so that also affects the over voltages. Now, what is the effect of these over voltages? These over voltages naturally cause, either they damage the power equipment, or some flashover may occur, some outage may occur, some fault may occur. So this may cause disturbances on the power system. Now, all the equipment connected to the transmission line or power system must survive due to these over voltages. Whenever voltages, you cannot 100% prevent them. So therefore, whenever these over voltages occur, our equipment connected to the transmission line should survive. So for that reason, we need to test before the installation itself whether the equipment survives or not. So there are certain testing voltages. Based on these over voltages, we need to test the power system equipment before installation or even during the manufacturing process also. So there are several testing voltages. Now, testing with power frequency. So this is the same as operating voltage frequency. So a little bit higher voltage we will test so that it will survive for some 30-40 years. So actually the life curve will be like this: Vt log V log T characteristics. So it is a straight line, log V log T. So for operating voltage, this is the operating voltage. To survive it for 30 years or so, now we are testing at T is equal to almost 0 at this instant. T is equal to 0, T is equal to very small, maybe 0.1 second, something like that. So it has to survive at this level in order to survive for 30 years or so. So as per this Vt characteristics. Therefore, at a little higher stress also we will test. So this is 1 minute duration actually. The tested duration will be 1 minute as per standards. So for 1 minute, the power frequency voltage is applied, and if it survives, then that is said to have passed. The equipment is said to have passed the power frequency test. Apart from this, there is lightning impulse voltage test and then switching impulse voltage test. We will see exactly what is lightning impulse voltage test and switching impulse voltage later after some time. So as I already told you, lightning impulse is the external over voltage, and the switching impulse is internal over voltage. Apart from these, tests will also be carried out on DC voltage testing. So for example, very long cable if you consider. So such a very long cable is actually a cylindrical capacitance. So it will absorb a lot of reactive power. So at power frequency, if we test, even though AC cable I'm talking about, even though AC cable, we need to test under DC voltages also. So what will happen when we test under AC voltage, it will absorb large reactive power is required for that one. So testing is very difficult from a laboratory voltage source. So for supplying so much of reactive power is not possible. So therefore, testing under DC voltages will also be carried out. Because under DC voltage, the cable behaves as an open circuit, so there will be no current except during the transition. There will be no current. So that's why DC voltage tests are carried out even for AC cables. But there were some apprehensions in testing under DC is not adequate. So after that, people have come up with very low frequency testing. So instead of completely DC, small frequency 0.1 Hz AC. So it corresponds to AC also, but at the same time it decreases the reactive power requirement because the frequency is very small. Therefore, VLF testing or very low frequency testing has come into picture. So these are the various testing voltages that are used for testing the power equipment. Now let us go to generation of these testing voltages in laboratory. So this is generation of high voltages in a laboratory. The scope of this presentation is to introduce you the circuits which will generate these high HVDC, HVAC and impulse voltages in a laboratory. What are those circuits? Basic principle only will be given, not advanced information, because actually whatever I am teaching you today is a half semester course, but I am giving you glimpses of various circuits only, not complete details. If I go into details, the depth is so much that it requires a lot of time. So therefore, I will introduce the concepts, how the high voltages are generated. Of course, these concepts are useful for even electronics students also, electronics faculty also, and electrical faculty also, because these same concepts are used in electronic circuits also to generate a little bit higher DC than from whatever we get, or high voltage AC, a little bit higher AC, or they generate pulses in electronic circuits. So these are circuits are useful for everyone, electrical or electronics engineers. So let me go and introduce the circuits now. So this is direct voltages or high voltage DC voltage, direct current voltage. Now the circuit, the figure here shown here is a Graaff-Walton circuit. It's called again on the names of the scientists who discovered this. So Graaff and Walton. So this circuit was one of the early particle accelerators responsible for the development of atom bomb. Also, the same circuit, using same circuit, these people have investigated, and several investigations were carried out on particle accelerations, and then ultimately it led to Nobel Prize also subsequent. So this is so important circuit where even now in all high voltage laboratories, almost all high voltage laboratories, HVDC generators use Graaff-Walton circuits. Of course, the same circuits are even available in electronics also for generating from maybe 5 volts to 10 volts, something like that, voltage doubler or voltage multiplier circuits. So before introducing that Graaff-Walton circuit, let us see what are all the other circuits which generate DC from AC. So AC to DC conversion, you may be knowing that half-wave rectifier. So here there is a transformer, and then there is a diode here, and it is connected to a capacitor. So if there is no load, what will be the voltage? If there is no load, the voltage will be simply the peak of this AC. If it is Vm sin omega t, then we will get Vm at the capacitor, just Vm. It is charged to peak plus minus here, Vm. And if there is a load, then the Vm will decrease. Of course, from here, it will decrease. Actually, it will decrease exponentially based on this time constant of this circuit, RC circuit. So from here, again, it gets charged when the voltage wave again crosses the voltage here. So again, it will charge and then discharge. So this kind of ripple you can observe the line. So this is how AC to DC conversion is done to get high voltage AC, but high voltage DC. But this circuit is limited to around 100 kilovolts maximum. Beyond that, the single circuit is not used. So other than this, we have biphase half-wave rectifier, or some people say it full-wave rectifier. Biphase, two-phase half-wave rectifier. Here, instead of one diode, we will have two diodes. So even in the negative cycle also, in the positive cycle also, we will be charging this capacitor, and then it will be converted into DC. So instead of once in a cycle, in the previous circuit I will show you, here only once in a cycle you are charging, but even the negative cycle also we will charge in this biphase half-wave circuit, half-wave rectifier. So after this, we have Alibon's voltage multiplier. So here you can see there is one transformer here. So this transformer here, two circuits are connected. One diode here and one capacitor here. So what will happen when the voltage is positive here, negative here? This capacitor C1 gets charged plus minus Vm here. Vm sin omega t. It is so plus minus Vm, it will be charged. And similarly, if you see upper part of the circuit, here, this diode through this capacitor will charge this capacitor also plus minus Vm. You can see these two capacitors C1 and C2 are connected in series, and here at this node the voltage will be 2 times Vm. Now after that you can see there is another transformer here, but that transformer is connected to this transformer using an isolation transformer here. So this isolation transformer and supplies the primary of this transformer. So same circuit is repeated. Whatever is at the bottom, using this transformer T2, again the same circuit is repeated. So again C3 gets a charge of Vm again here plus minus Vm, and C4 also gets a charge of plus minus Vm. So total we have multiplied the voltage to 4 times V. 4 times Vm. Vm is maximum voltage of sinusoidal voltage at the secondary side of the transformer, T1 or T2. Both are same voltage only. So this is how the voltage multiplication has been done here. Although we are getting from secondary of the transformer Vm sin omega t. So using two transformers T1 and T2 and one isolation transformer here, so which simply isolates the circuit. So we are able to get, or we are able to multiply 4 times the voltage. So this is proposed by Alibon, a scientist. Then after that, see, any further simplification is possible. Just think about it. Yeah, so it is possible that can we avoid this isolation transformer? Yes, it is possible. I will show you how it is done. So this is a DC cascade circuit with transformer here. Instead of having an isolation transformer, that isolation transformer is replaced by a third winding on the T1, that is your tertiary winding, again which will be driving the primary of the T2. So this is how the isolation transformer is removed. Now this system can be used to arrange any number of cascading circuits here. So any number of units can be done this way. In previous case, the problem is in Alibon circuits case, if you extend this to further stages, you need more and more isolation transformers, and then this primary will be loaded. This first one will be loaded much. So therefore, if you have this kind of arrangement, now obviously, so you can cascade any number of transformer. Of course, loading effect will be there here also. So this way, the voltage V plus V, if there are n stages, n times 2V. So one stage is considered to be like this much. So n times 2V can be the voltage at the output. So this is how high voltage DC can be generated. But here you see so many number of transformers are used. So is there any other way to avoid these transformers? So that is the next step, that is Graaff-Walton voltage generated. before going to Graaff-Walton, we will simply see the voltage doubler circuit. So I am drawing here the voltage doubler circuit. This is a transformer here, and there is a diode here. If you can see, one capacitor. So this simply what will happen. This is just half wave rectifier. But if you add one more capacitor here, don't ground the middle one. So now this capacitor you ground it. Okay. Now using a diode, you connect this terminal to this terminal. Here there is no connection, like this. Now what will happen? So this capacitor will be charged during positive half cycle, say plus minus Vm, and the other capacitor will be charged during negative half cycle, plus minus Vm again. So total voltage is 2 Vm. So this is voltage doubler. This was the primitive circuit. Even before Graaff and Walton, Graaff has proposed this circuit. Actually, Graaff circuit is the building block for Graaff-Walton circuit. So now this same circuit, this is voltage doubler, is the first stage of Graaff-Walton circuit. If you carefully observe this capacitor, and then this is the second capacitor, which is again charged. So here what will happen? This first capacitor will get charged through this path, plus minus Vm, and again the second capacitor gets charged during the second half cycle. So like this way, the first capacitor will be used to charge the second capacitor, and here you will get plus minus 2 Vm. So this is one stage of Graaff-Walton generator. So now this is repeated. The same is repeated. Again, when this is charged to 2 Vm, again through this diode, and when this voltage source goes through, plus minus here maximum, the total voltage applied is 3 Vm. That will charge this capacitor to again 2 Vm. So like this, if this goes on multiplying the voltage. Of course, only this capacitor is charged. First capacitor here is charged to Vm, second capacitor to Vm, and then all other capacitors in this branch will be charged to 2 Vm. Again, in this branch, all other capacitors will be charged to 2 Vm. So like this, if there are n stages, total voltage that can be obtained is 2 times 2n into Vm. So this is how the voltage gets multiplied in a Graaff-Walton voltage source. So this is how high voltage DC is generated in a laboratory using several stages of this one. Why several stages? There may be a question. Why not a single capacitor? And then there is a limit actually. One is the size limit for manufacturing. Of course, it is practically not impossible. You can make it. What is there? You can make it. You have to design and then. But the problems that will arise is you have to transport from manufacturing location to a laboratory where the circuit, where the source is to be used. So for transporting, the size is limited by trucks. You have to transport. So there are problems associated with that. Also, manufacturing cost also. If it is small size components and then multiple number of components are to be manufactured, then the cost will be small. So same, and you can also extend it further. For example, initially you have ordered 10 stages, and then you want to extend it. Then obviously you have to just multiply the circuit. So you can order further stages and then increase the voltage level. That is also possible. So due to these advantages, normally these circuits are made as multiplier circuit, voltage multiplier circuit, not as a single unit, single circuit. So apart from these, electrostatic voltage generators are also available. These were actually original primitive main circuits that were initially developed. So here, what is done is simply charge is lifted mechanically and then put it on a spherical electrode. What will happen? Suppose a spherical electrode is there and it is above the ground. So it will have certain capacitance C, right? So now Q is equal to CV, Q equals to CV. Now for voltage V, it is Q by C. Suppose if there is no charge on this capacitor, the voltage is 0. But somehow you brought some charges and kept it on this spherical electrode. What will happen? Its voltage will increase depending on the charge. So suppose its capacitance is C. Capacitance means capacitance to ground. This spherical electrode and the capacitance to the ground. If it is C, then Q by C is the voltage. Now, if you go on increasing the charges, then obviously the voltage will increase. But how to bring the charges and keep it on the spherical electrode is the question here. So that is what is achieved here. Me delete these things. Now here there is a spherical electrode centrally. You can see that is the high voltage electrode. So now what we are doing here is there is a sharp electrode here and there is small voltage source. It is also a voltage source. It is of course roughly around 10 kilovolts can be used maximum. So to generate high voltage DC, we will again use DC only, small voltage DC. So here, using this 10 kilovolts and a sharp electrode, what will happen if a sharp electrode is given very high voltage? What will happen here is, at this sharp end, you will get the charges coming out due to ionization and breakdown, what is known as corona. So, or discharges. So the discharges will occur at the tip of the electrode. Same concept is used here to get the charges, and these charges will come out at this sharp electrode, and we will arrange in such a way that these charges get deposited on a belt. Now you can see this is the belt. So belt moving, rotating in this direction, direction shown in the arrows like this. So what will happen? So the charges will be deposited on the surface of the belt, but the belt is moving up, and then these charges, how the belt is moving up? By mechanically driving it by a motor. You can see here there is a motor arrangement which will with a shaft which will mechanically drive the belt, and the belt will be moving upwards. So in a way, what is happening is the charges are being lifted up and kept on the high voltage electrode here. But how they are kept on the electrode? Here there are, you can see at the upper fully there is a collector here. Collector is nothing but again a sharp electrode only, which will absorb the charges here. This is the collector, and this is again upper spray point. This will again spray the negative charges on the belt, of course. So this is how physically we are lifting the charges and keeping them on the spherical electrode, high voltage spherical electrode. So therefore, V is equal to Q by C. So as charge increases, the voltage increases. So this is how the high voltage is generated. And compared to the previous case where we have used multiplier circuits, in this case the voltage is pure DC. It's not fluctuating or ripple content will not be there. Pure DC can be achieved here. So this is the Oak Ridge National Laboratory. You can see the height by comparing the size of this ducts. it is around 20 megavolts that Van de Graaff generator generates here. So this is how electrostatically voltage can be generated, and this is smooth DC, and high voltages can be generated. Of course, we need higher and higher size. There are certain challenges such as corona coming out and then discharges to the load, etc. So those are specific details that can be studied in any book. Now, until now we have covered the DC voltages. Now alternating voltages. Alternating voltages are very simple to generate. Alternating voltage already we get in a laboratory 230 volts AC. So in order to generate high voltage, what is to be done? Naturally we have to use transformers. So that's what is done actually to generate high voltages in a laboratory. These are single units, and with this kind of construction, around 100 to 150 kilovolts only can be generated. So there are two types of constructions given here. This is metallic body actually, metallic body, transformer, metallic body. And here, this is insulating body, insulating. So due to this insulating and metallic body, there are minor constructional details. Apart from that, nothing is different. Both are same. So when metallic body is used, when you are taking high voltage terminal, you have to use such a construction which is known as bushing. You might have seen, outside also transformers having such a construction. So there is, porcelain insulators you must have seen outside. So, and the high voltage lead is taken through this bushing inside using pipes, and then here a spherical electrode is kept, which is at high voltage. So this is the arrangement which is needed for metallic body. That this is the same is not needed because this body is insulating body, already insulating. So you can use high voltage electrode like this simply, and by connecting it to the high voltage winding. This is first primary winding, and this is secondary winding. So primary winding and secondary winding, one above the other. So in order to reduce the leakage, so one above the other it is wound, and then just only one leg here. This is the core, and inside this oil is used. Transformer oil it is called. It is petroleum based oil actually. Similarly, in this transformer also same oil is used. Here also one single core is there, and then on that primary circuit, above that the secondary winding is there. The trapezoidal type of winding arrangement is to avoid, in transient condition, equal distribution among the winding layers is required. So for that purpose, these windings are made into trapezoidal construction, not simply cylindrical construction. Looks like cross section looks like trapezoidal. Now here we have representation of the same thing with a primary here and then secondary here. This is how single units up to 100 to 150 kilovolts, this kind of designs are used. So if we want to multiply here, actually the core is at ground potential, you can see. The core is at ground potential. And one winding of the high voltage is also at ground potential. One winding of the primary winding is also at ground potential. So this is the designs for up to 150 kilovolts. Now for a little bit higher voltages, so these are the practical equipment, transformers. This is metallic body again. This is insulating body. Insulating body means this is simply paper tube actually. Paper tube means, paper is wound several layers using adhesive. So it will be very strong. Paper tube means it's not, easy to mold also. It is very strong, like a metal only. Of course, certain advantages and disadvantages both are there. So here the metallic body actually conducts the heat outside very easily, but that is not the case in case of insulating body. But this requires a bushing type of construction and huge height, etc. That is not required for an insulating body. So these are two types of constructions. Now single units up to higher voltages, there is a small constructional change here. What is done is winding is split into two parts, and instead of grounding the core potential, the core will be at the midpoint potential. The midpoint of the winding is connected to the core like this. You can see. So that 50% is here, 50% is above. So that the voltage, without changing the insulation, we will achieve voltages up to 300 kilovolts. So insulation level without changing that, we can achieve up to 300 kilovolts. Because the maximum voltage difference between core and any lead will be around 100 kilovolts only. So that is how the insulation, for the same insulation level, we can achieve double the voltage almost. So this is another type of construction for generating high voltages using just single units. But as I have pointed out, in case of DC, we need multiplying circuits because 300 kilovolts is not at all sufficient to test the power equipment insulation. We have to, for extra high voltage, we need thousands of kilovolts, even megavolts generation. So for such kind of voltage generation, we do need multiplying circuits. So this is how the cascaded transformer set. Here you can see there are three transformers. This is transformer 1, transformer 2, transformer 3. So these three transformers are cascaded here. Now each transformer, you can see there is a primary winding, there is a secondary winding, and there is an auxiliary winding here. So three windings it has. This auxiliary winding is to drive the primary of the second transformer. So like this, three transformers are cascaded here. So what will happen? The secondary voltage, the first transformer is V, and the second transformer, secondary is connected to the top end of the first transformer secondary. So that's how the voltage gets multiplied here 2 times 2V. And if you use another transformer like this, here again, this becomes 3V. So like this, if you have N transformers connected in series, you can generate NV at the output. But this has certain disadvantages, of course. For other power equipment other than cables, it can be used, but for testing cables, it creates some problem. What will happen, so the reactance. So when you are cascading like this, the primary reactance will appear in the secondary reactance will appear in the other transformer secondary, like that. So the effective reactance, for example, for 3 stages becomes, it is not simply 3XH and 3XE plus 3XP. So XH means high voltage winding reactance, XE excitation winding reactance, this windings reactance, and then XP is primary winding reactance if you assume. It is not 3 times XH plus XE plus XP. It is in fact the reactance seen at the secondary side, completed output side, is 3 times XH plus 5 times XE plus 14 times XP. So this is how the reactance gets magnified like anything. What will happen if reactance gets magnified and you are testing a cable? Cable, as I told you, is a capacitor. Now this huge inductance and then cable capacitance will be in series. Therefore, that may cause resonance at a particular frequency. So I'll show you. So the equivalent will be a high voltage source like this, and then huge reactance, inductance, then capacitance like this. So this may cause resonance. At power frequency also depending on the length. If not at power frequency, some harmonics also may get multiplied. So the voltage seen at the test object, this is cable or test object. At test object will be different under resonant conditions. Very high voltages are expected, and that may cause breakdown. So this actually happened in field. Initially, cascading transformers were used for testing the power equipment. What happened when they were testing the cable, premature failures were observed. Why the failures? After that, lot of investigation was done, and then they found that resonance is occurring in the transformers. So this is one of the major disadvantages. You may be thinking no load voltage a very small value, but very high value will be applied due to resonance condition. So obviously cable will break because voltage is more than normal voltage. So to avoid this problem, the same concept is used in the next generation transformers. These are cascading transformers. The next generation transformers, sir, of course, these are the figures of cascading transformers. This is General Electric Company at Pittsburgh. You can see 3 transformers here. So these are cascaded. The primary is the first transformer is driving the second transformer, second is driving the third transformer. Similarly, here also you can see the CPRA circuit here. There are also two transformers here, and then they are generating high voltage. Now, as per the resonant transformers, these are the next generation transformers. So the disadvantage observed in the case of cascading transformers is again overcome by using the same concept is used to generate high voltage. Why don't we use the same resonance to generate high voltage instead of cascading the circuits? So same way, what is done, this is the feed transformer and this is the test object. Test object is always capacitive in nature. So what you do is, we have to change the inductance here in such a way that resonance is achieved here. So the resonance is intentionally achieved here to generate high voltages. But how to achieve the resonance? You have to change an inductance. But inductance connecting in high voltage circuit and then changing there is ruled out. So what is done is a transformer is used. The transformer primary side you connect a reactor. Obviously it will reflect at the secondary side. Impedance transformation you may be knowing. So primary side we will connect the small reactor which is at low voltage level, and then we can change the reactance at the low voltage level, and that will automatically get reflected in the secondary side. So we will adjust the reactance in such a way that actually automatically it will be adjusted. We don't even be touching that one. To achieve the resonance condition, and under resonance condition high voltage will be applied here, and after achieving the resonance condition, again regulator transformer is used, and slowly whatever required voltage will be achieved by changing the regulating transformer voltage. So this is how high voltage AC is generated in a laboratory using resonance principle. So after this is the concept actually. Now similarly, so 3 reactors can be cascaded like this, or 2 reactors here can be cascaded. This is another principle, actually I should say. Here instead of changing using a transformer, here mechanically using a mechanical drive which will change the core or air gap in the core and adjust the reactance value here, or changing mechanically by using a mechanical drive under. So this is the difference is only in the mechanism how we are changing the reactance of the inductor to achieve the resonance. But this is transformer action. This is better one in my opinion. So this is how using the resonance principle, the equivalent circuit is given here. So there is an inductance L which is variable. Variable may be any of the principles mechanically or transformer you can use. And there is a load here, capacitance. The small resistance is resistance of the circuit winding itself. So this is how the resonance is achieved in a laboratory to generate high AC voltage. So these are the resonant transformers you can see. This is Akhil Electronics, India in Gujarat. It is. You can see the height, etc. of the resonant transformers. There are 3 transformers it seems. And here, this is again Hitachi, Japan. Actually, where in this laboratory I worked actually. So this is very high voltage generator again. So using the resonance principle. Now, this again resonant transformer only. Power HV is the company which installed. This is outdoor resonant transformer. This is the physical size of transformers for testing. You can see. Now, again, one more principle is variable frequency resonance. So instead of changing the inductance, change the frequency here to achieve the resonance. Because if you change the frequency, if you go on increasing the frequency, omega L will be increasing, 1 by omega C will be decreasing if you increase. So at some point of time, these 2 reactances will be equal. That is the resonance condition. So that's how using variable frequency also resonance can be achieved. But of course, there are concerns that you are not testing at the power frequency, right? So normally power equipment will be operating at power frequency. So that's why this is one of the disadvantages of this. Now the last one is lightning or switching impulse voltage generation. So the circuits, actually there are 2 types of impulse voltages I already told you. One is lightning, this transmission line tower you can see here. This is lightning. Another switching, this is circuit breaker when it opens or closes or fault condition. So this is the lightning standard impulse and then this is the switching standard impulse. Only the times are different. 1.2 by 50 microseconds. 1.2 is the time to reach the peak and then 50 is the time at this time. So 50 microseconds. 1.2 by 50 microseconds is lightning impulse. Lightning are, shorter in time than switching. Switching is actually 250 to 2500 microseconds. 250 is the front time and then 2500 is the time to tail. So these 2 are standard lightning and this is standard impulse, standard switching waveforms. Apart from these, you have, sometimes the breakdown may occur or flashover may occur in between, somewhere in the either tail or front chopped off. So this is how the actual waveform may be chopped off. This is in front and this is here in tail side. So the waveform depends on where exactly it gets chopped off due to flashover or due to breakdown or whatever. So these 2 impulse waves are to be generated in a laboratory. So for that purpose, we have different kinds of circuits here. 2 different kinds of circuits are shown here. So the concept is very simple. A capacitor is charged and then this gap is triggered. What will happen? This, R1 is smaller than R2. So this will charge this capacitor initially. So the voltage is the output voltage taken is here across the C2. The voltage across C2, the moment you trigger this gap, the voltage across C2 will rise. And after reaching the peak, again, the C2 will discharge through this circuit basically. Of course, the other part also will discharge, but basically it will discharge through R2. So discharge means the voltage will decrease. Initially it will rise and then decrease. So this kind of waveform, known as double exponential waveform, is generated using this circuit. Similarly, this circuit also. So during charging, it will charge like this. During discharging, it will charge like this. Only that the R1 will also come in series with R2 when it is discharged. So this is how, basically I am explaining the basic concept. Actually, the phenomenon is a little bit complex. you can obtain exact solution using this, analyzing this circuit. Actually, you will get V0 by K 1 by alpha 2 minus alpha 1 into e to the power of minus alpha 1 t minus e to the power of minus alpha 2. This is how the output voltage you will get here. So actually it consisting of two exponential waves. One is decaying like this, another is decaying like this. In effect, the sum resultant will be like this. A double exponential. So this is also generated in using multiplied circuit again. So this is Marx circuit in which all the capacitors are charged in series and then they are discharged in parallel, so that the impulse wave like this is generated. I'm running out of time. So this the concept is very simple. I will explain the concept using this. So here DC is used. So when DC is used and then this, suppose the gaps are not triggered, what will happen ultimately? For a long period of time, if you keep this DC applied here and then leave it, what will happen? All these capacitors will get charged to the DC voltage plus minus Vm. The moment you trigger these gaps, sphere gaps, what will happen? All these will be connected in parallel. Earlier they were in series. Earlier they were in parallel. They charged in parallel to plus minus Vm. But the moment you trigger these gaps, these capacitors will get connected in series. So high voltage will be generated. So that voltage, these capacitors will charge this C2 during the their discharging period. And after this C2 reaches its peak, again the C2 gets discharged through this path. So this is how a double exponential wave is obtained using this Marx circuit. These are multi-stage circuits, they are called, are used in every high voltage lab. 5,000, 6,000 kilovolts or 5 or 6 megavolt generators are also available. So, but sometimes we may need oscillating waveforms also. So in order to get oscillation, the same circuits, whatever I have shown, simply introduce some inductance here, you will get oscillations like this. Why these oscillations? Actually in transmission lines also such kind of oscillations will come. So to test the power equipment, some customers may demand that the equipment may be tested using these waveforms. So for that purpose, you generate these waveforms in the laboratories. So these are oscillating impulses. So these are the typical impulse generators. You can see this is 3200 kilovolts in Switzerland, Hoffley, made by Hoffley. Very huge height. You can see the height of a human being here. So human beings are normally kept in high voltage photographs in order to compare the size actually. How big the equipment is. So similarly, this is 1600 kilovolts by same Hoffley. This is old circuit and this is the latest actually. And then this is another circuit from some Chinese company. So we also have a small impulse voltage generator. It is around 440 kilovolts at IIT Roper. So this is my presentation. It's the end of the presentation. Thank you very much. Now open for questions.